Training teaches a model everything it knows, but inference is the moment that knowledge becomes useful. Inference is the process of running a trained model on new, previously unseen inputs to produce outputs. Every ChatGPT response you receive, every image generated by DALL-E, every code suggestion from GitHub Copilot is the result of inference. Unlike training, which happens once and takes days or weeks on thousands of GPUs, inference happens in real time, potentially millions of times per day, for every user of every AI application. Understanding inference is therefore not just an academic concern. It determines the latency users experience, the cost organizations pay, and the architectural decisions that make AI applications viable at scale. Let us examine the mechanics of inference in large language models and the key engineering challenges that organizations must address to serve AI responses reliably and cost-effectively at scale. 5 core aspects of inference define how LLMs generate responses and why serving them at scale presents such significant engineering challenges. The forward pass is the core computation of inference. When you send a prompt to an LLM, the tokenizer converts your text into a sequence of token IDs. These are embedded into vectors, which flow through each of the model's transformer layers in sequence. In each layer, the self-attention mechanism computes how each token should attend to every other token, and the feed-forward network further transforms each token's representation. After all layers, the final layer's output vectors are projected onto the vocabulary to produce a probability distribution over all possible next tokens. This entire computation must complete in milliseconds to deliver a responsive user experience. Unlike a classifier that produces a single output from a single forward pass, an LLM generates text autoregressively, one token at a time. After the forward pass produces probabilities for the next token, a token is sampled from that distribution, either the most probable token, greedy decoding, or a token drawn probabilistically, sampling with temperature. This newly generated token is then appended to the context, and the forward pass is run again to generate the following token. This process repeats until a stopping condition is reached, typically a special end-of-sequence token or a maximum length limit. Generating a 500-word response may require 600 to 700 individual forward passes, each building on the previous. Individual inference requests are inefficient to process one at a time because they leave GPU compute largely idle between tensor operations. Batching solves this by grouping multiple independent inference requests and processing them together in a single forward pass, amortizing the fixed overhead of loading model weights and maximizing the utilization of the GPU's parallel compute capacity. Dynamic batching, grouping requests that arrive within a short time window regardless of their originating user, is a standard technique in production LLM serving systems. Continuous batching, introduced by systems like VLLM, goes further by allowing new requests to join an ongoing batch mid-generation, dramatically improving throughput. In inference system design, latency and throughput are fundamentally in tension. Latency is the time from submitting a request to receiving the first token of the response. Users experience this as responsiveness. Throughput is the number of tokens the system generates per second across all users. The operator experiences this as cost efficiency. Optimizing for low latency often means processing requests individually with large, fast hardware, which is expensive. Optimizing for high throughput means batching aggressively, which increases the wait time for individual requests. Production AI serving systems must be carefully tuned to find the right operating point for their specific user experience requirements and cost constraints. Running inference for large LLMs requires specialized hardware. A 70 billion parameter model in 16-bit precision requires approximately 140 gigabytes of GPU memory to load the weights alone, exceeding the capacity of a single GPU. Multi-GPU serving using tensor parallelism, which splits the model's weight matrices across multiple GPUs, is necessary for such models. NVIDIA's A100 and H100 GPUs, with 80 gigabytes of HBM2E and HBM3 memory respectively and thousands of CUDA cores, are the workhorses of commercial LLM inference. Google's TPU v4 and v5 chips offer an alternative optimized for transformer workloads. The hardware cost of inference is one of the primary drivers of AI service pricing. 4 essential terms for understanding how AI inference works and what determines its performance characteristics. During a forward pass for an LLM, the input token IDs are first converted into embedding vectors by looking up a learned embedding table. These embedding vectors, combined with positional encodings, are passed through a stack of transformer layers. Each layer applies multi-head self-attention, layer normalization, and a position-wise feed-forward network. The output of the final layer is projected through a language model head, a linear transformation followed by a softmax, to produce a probability distribution over the entire vocabulary. This entire computation is parallelized across the GPU's thousands of compute cores, enabling it to complete in milliseconds even for models with billions of parameters. Autoregressive generation is what makes LLM output sequential and coherent. Because each token is generated conditioned on all preceding tokens, the model can maintain narrative consistency, track entities mentioned earlier in the conversation, and progressively build complex arguments or code structures. The key-value cache, or KV cache, is an important optimization that avoids recomputing the attention keys and values for previous tokens on each generation step, instead caching them and reusing them, dramatically reducing the computational cost of autoregressive generation for long sequences. Without the KV cache, generating a 1,000 token response would require 1,000 full forward passes over the entire growing context. Latency is the user-facing performance metric that determines whether an AI application feels responsive or frustrating. It is typically decomposed into time to first token, the delay before the response begins streaming, and inter-token latency, the time between each successive token. Time to first token is dominated by the pre-fill phase, in which the entire input prompt is processed in a single forward pass to populate the KV cache. Inter-token latency is driven by the decode phase, in which one token is generated per forward pass. Streaming responses, displaying tokens as they are generated rather than waiting for the full response, dramatically improve perceived latency for users even when total generation time is unchanged. Throughput is the primary metric that determines the cost of running an inference service. A system that generates 1,000 tokens per second at a hardware cost of $1 per hour has a cost of 1/10 of a cent per 1,000 tokens. Throughput is maximized by batching requests, minimizing idle GPU time, and using hardware with high memory bandwidth, since inference in LLMs is memory bandwidth bound rather than compute bound for large batches. Inference optimization techniques, including speculative decoding, using a small draft model to generate candidate tokens that are verified in parallel by the large model, can significantly increase effective throughput beyond what sequential decoding alone achieves. Let us now examine the practical landscape of AI inference, from managed cloud APIs to local inference tools, and the optimization strategies that make large-scale deployment economically viable. 4 distinct approaches to deploying AI inference reflect different trade-offs between capability, cost, latency, and data privacy. Managed inference APIs are the simplest and most accessible way to integrate AI capabilities into applications. OpenAI, Anthropic, and Google each offer REST APIs that accept a prompt and return a model-generated completion, handling all infrastructure, scaling, and model management automatically. Developers pay per token consumed rather than provisioning and managing GPU infrastructure. These APIs provide access to frontier models, GPT 4.0, Claude 3.5 Sonnet, Gemini 1.5 Pro, that organizations could not feasibly run themselves due to the infrastructure requirements. The primary trade-off is that user data leaves the organization's control and is processed by the API provider, which creates privacy and compliance considerations that must be carefully evaluated. Local inference, running AI models on hardware that the user controls, is increasingly practical for models up to 70 billion parameters thanks to quantization and efficient inference frameworks. Llama provides a simple command line tool and REST API for running open-source models like Llama 3, Mistral, and Gemma locally on Mac, Windows, and Linux machines with consumer GPUs. Llama.cpp, written in C++, enables CPU-based inference for quantized models on hardware without any GPU at all, making LLM inference accessible on ordinary laptops. Local inference eliminates data privacy concerns, removes per-token costs, and enables offline operation, at the expense of lower capability compared to frontier cloud models. Inference optimization is a rapidly evolving engineering discipline aimed at reducing the cost and latency of serving AI models without degrading their output quality. Quantization reduces the memory footprint of model weights, allowing larger models to fit on available hardware and reducing memory bandwidth requirements during generation. KV caching avoids redundant recomputation of attention keys and values across generation steps. Speculative decoding uses a small, fast draft model to generate candidate token sequences that are then verified in parallel by the large target model, increasing effective throughput. Flash attention rewrites the attention computation to be more memory efficient, reducing both memory consumption and latency during the prefill phase. For organizations building AI applications, inference cost is one of the most significant operational expenses and must be modeled carefully. API pricing is typically expressed in dollars per million input tokens and dollars per million output tokens, with output tokens generally priced 2 to 5 times higher than input tokens. A customer service application that handles 1 million queries per day, each consuming 500 input tokens and generating 200 output tokens, might spend tens of thousands of dollars per month on inference alone. Cost optimization strategies include prompt compression to reduce input token counts, caching common responses, routing simpler queries to smaller and cheaper models, and batch processing non-real-time tasks during off-peak hours when spot pricing may be available. Let us bring together the essential points from our exploration of AI inference. To explore more key concepts in generative AI, check the link in the description. If you found this helpful, please like and subscribe. Thank you for watching. If you found this helpful, please like and subscribe. See you in the next video.